Okay, so let's get started. Congratulations to all of you who made it to the last lecture, to the war of attrition. Today it'll be pretty casual. Just going to go over a few topics that I think are good for people to know, whether you do MRI or not. It's just sort of nice to know certain things about MRI because my guess is most of you will have some sort of MRI done in your lifetime. And so this just might be of interest to you. And then feel free to ask questions if there's something pertinent to your project or something you want discussed or something, we can certainly do that as well. Okay. So any general questions before we get started? Okay. If not, let's dive in. So today we're going to talk about imaging of flow. So last time we talked about diffusion. Today we're going to use similar concepts to talk about flow and just give you a taste of, um, how flow is imaged. I think in the news, obviously, MRI was in the news lately with the president's discussion of his MRI or non-discussion of his MRI, and most likely there was some imaging of flow in those exams, and so hopefully get a better feel for that. We'll touch a little bit about noise in SNR, just so you have a sense of that, and then we'll talk about some future directions and sort of what to expect. Certainly things that are going to happen in the next 5 or 10 years, what direction things are going to go in. Okay, so let's just sort of give you sort of a sense of how do we image flow with MRI. And so once again, it's like last time, we're going to consider two spins, A and B. And we're going to assume that spin A stays stationary and spin B is moving. And instead of random motion like we did last time, we're going to assume that there's sort of like a flow, a velocity in a certain direction. And what we want to do is measure that velocity. Okay. So A is going to be stationary, B is going to be moving at a certain velocity. And so once again, we apply this gradient. So this is like a minus GX gradient, right? Because it's a negative slope. And so what we expect is after some amount of time, spin A will have, let's say, gone counterclockwise 90 degrees, and spin B goes even more counterclockwise. Okay. Because notice it's moving into a stronger part of the field, right? So it's going to accumulate more phase because it's starting to process faster than spin B. All right. And then we wait some amount of time and then we reverse the gradient. So now we've got a plus GX gradient. And so spin A is going to get totally refocused, right? Because whatever gradient it experienced for the first half, it experienced equal and opposite gradient, right? So if you imagine what the gradients are look like, we're turning on a negative gradient and then we're turning on a positive gradient. Okay. And so the spin A just experiences the net sum of those gradients, which is zero. Okay. But you notice what happens to spin B. Um, it moves into a more positive part of the gradient. And so when it comes, it sort of does a clockwise rotation, okay, that way, but it overcompensates, right? Because it's got experiencing much stronger fields than it needs to do to refocus. All right. So it's as if during the first part it experienced a negative, and then the second part experienced a much bigger positive, right? Because it's moving into a much stronger part of the gradient. In fact, if you were to think about it, it would look something like this. It's sort of experiencing a linear increase in the gradient and then an even more linear increase that way. Okay. So that means that there's a net phase that is proportional to the velocity. Okay. And so this is where the phase of the spins actually becomes a really important piece of information because it's going to tell us what the velocity of the spin is. Uh, so remember the phase can be written as the integral of the change in frequency. Okay. And these then that's related to gamma times the delta field. And that's just given by the dot product of the gradient and the position vector. Okay. So this is sort of, we've seen this before, like a gxx plus gyy plus gzz. Okay. And previously, we've assumed that these are time independent, right? But now what we want to consider is what happens if, x. of t has time dependence, right? right? The position is changing with time, right? So what we can do is we can write a really simple model going back to, high school or freshman physics. We're going to say the position of my spin has some initial position plus some incremental position due to its velocity plus something due to its acceleration. Okay. And for today, we're just only going to focus on the velocity term. Okay. So what we can do is we can replace this time the x of tau with this expression here, and then we just plug it in. And so we're essentially multiplying the gradient by this expression for the position. And you'll notice we get a few terms. One term is what we looked at, we were very familiar with, which is just the area under the gradient. Okay. And so that's where that refocuses and that area goes to zero. And this tells us where we are in K space. And that integral is called the zeroth order moment. And then the term we're going to really focus on here is we also have another term, the gradient times the time integral of that, and that gives us the first order moment. All right. So you've probably heard about first order moments in physics. And so now we're looking at it in context of MRI. So what we're going to really see is that the first order moment is going to determine the phase, because basically we're saying that the phase depends on gamma times the velocity times that first order moment. Okay, so that's what we're really going to care about. And if you think about from a point of view of physics, like a first order moment is like if I have like a beam here and I think about the forces that would make this beam rotate, like if I have a force going this way and a force going this way, that's clearly going to make that beam rotate, right? So that's got a first order moment, right? But it has a zero order moment because equal and opposite forces like that. Okay. So the main thing is that we're going to focus on this zeroth order moment, first order moment. Okay. That's because that's going to multiply our velocity term. So let's take a look at what that first order moment looks like. So remember here we have what we call, these are typically called bipolar gradients. And so typically we'll turn it on for some amplitude for some time t, and then we'll reverse the sign and then have it on for the same amount of time t. So we want to look at the properties of that pair of gradients. And so first of all, what we said before is that the zeroth order moment is just zero, right? Because the sum of that area is zero. And then the first order moment, we can go through the algebra. And if you go through that, it turns out to be G0 times t squared. Okay. So the bigger you make the gradient, the bigger the first order moment. And also the longer you make it, it's got a quadratic dependence. Okay. So the nice thing is in MR is we control both of these. Okay. User control. Right. So we can set the first order moment by setting the gradient and also how long it's played out for. So this is sort of an example of what the phase looks like. So if I have a stationary spin, right, it accumulates phase, but then I refocus it. So at the time of the end of those pulses, I have zero phase, right? In here, I'm accumulating negative phase, but then I overcompensate and accumulate much more positive phase than I need. And so I end up with a net phase. All right. So that's the picture we looked at before. And then what you can also do is to sort of make the technique more robust is you can acquire a phase with one first order moment. So let's see, what was that negative? Okay. Um, yeah. So anyways, the phase here is we're going to get one phase from one set of gradients with them flipped one way, and then we can flip them the other way and get the equal and opposite phase. And if you take the difference of those two phases, it subtracts out sort of background effects, and you can get sort of this phase here. But the main thing is you can always relate your delta phase to something that's related to your velocity and some first order moment. And then what you do is you solve for the velocity. Okay. So we're going to measure the phase. We're going to measure this. And then this is what we measure. This is what we control. And then we can solve for the velocity. All right. So that's the basic idea. And we'll show you some examples of that now. So this is some examples of what a phase. So this thing is called phase contrast angiography. Okay. And what we're showing you here is basically, let's zoom in on this. So this is looking at sort of through your neck. Okay. And so this is an axial scan through your neck. And what we're looking at is the phase of the carotids here. So this is one carotid and another carotid. And also you're looking at the jugulars, right? So it's sort of, and the black is one velocity in one direction and the white is velocity in the other direction. So that makes sense, right? I mean, if that wasn't the case, this person would have problems, right? So clearly, if the velocity is going this way in the carotids, and then it's going this way in the jugular, the veins. Okay. And also there's also these vertebral arteries here, sort of at the back of your neck. And you can sort of see here the velocity is not as strong as it is in the carotids. So typically the flow in your carotids is the strongest, right? So that's like if you get, you know, you're in a martial arts movie or something and someone slices your carotid, you're going to bleed out very quickly, right? Whereas if they slice your vertebrals, it's not going to bleed out as quickly. Okay. And so then you can actually, with MRI, then you can actually look at the velocity across the cardiac cycle. So this is across the cardiac cycle or part of the cardiac cycle. Okay. And so these are your left and right carotids. And this is the flow in centimeters per second. So you can sort of see the flow is actually pretty fast through your carotids, right? It's getting up, the peak flow is around 45 centimeters per second. Okay. So that means in 1 second, it goes, 45 centimeters, which is quite a lot. Okay. And then these are your vertebrals. And you can sort of see the flow is about half of that much. And there's some difference between the left, right arteries there, but not huge. Okay. So that's one idea. That's one sort of picture of phase contrast angiography. Here's another example where you can sort of see that we have the white is showing flow in the anterior posterior, so from the front to the back of the brain. And you can sort of see here there's flow going back here. So there is flow going to the back of your brain. And then here, this is the left-right flow. And so you can sort of see here, this vessel is flowing this way, and this vessel has blood flowing that way. Okay. So yeah. And then here, I don't remember exactly what this is showing, but there seems like be something wrong with this one because the blood is flowing in the wrong direction. It should be going out that way. Okay. The other thing you can do, and I'm not sure there's going to be a project on this, but you can actually measure flow. Remember, the gradient just tells us the flow in a certain direction. So you can actually look at the flow. You can turn on the X gradient and look at the flow in the X direction. Then you can also look at the flow in the Y direction and look at the flow in the Z direction. So you can measure all different components of the flow. And you can also do this, for example, this is like timing to the cardiac cycle, and you could look at it at different parts in the cardiac cycle, like we just showed. And an application of that is you can look at like blood flow in time. And so this is what's called 4D flow. Okay. And here's a nice movie of that. And so 4D flow has been around for, probably 30 or 40 years, but it turned out that it's not till maybe the last 10 or 15 years that it's become much more popular. And part of that is sort of the processing always took a lot of time. And it wasn't until one of the people who took this class about 20 years ago was one in the first class of this first session of this class when he was a medical resident, he went off and started a company, and because he played a lot of video games, he actually was using NVIDIA chips and GPUs before the whole deep learning thing, and so this actually spun off into a company that is still doing this stuff. So there's a lot of opportunities for, even if you're into video games, and the other really interesting thing is that GPUs were really developed for video games, right? And it wasn't until later that NVIDIA had the really, amazing insight actually to realize, oh, these are going to be really great for AI, and therefore that's why they're $1 trillion company now or something like that. But the other industry, lots of industries have benefited from this, but medical imaging has benefited from this a lot. Okay, because there's so much, as you've seen with the recon and everything, there's a lot of computation that goes on, and so um, with each generation of magnets or MRI systems we get, we sort of see, oh yeah, there's more GPUs. Okay, and so when you're getting your scan done and you get these images, you have sort of the video gaming industry to thank for that because without that pressure, I don't know if the GPUs would have been developed. Okay. One thing that you should know about is that remember we're looking at phase, right? And we're saying that the phase is basically proportional to velocity. So if I had a phase, I could have a phase of pi if the velocity went this way, or a phase of pi if the velocity went that way, right? And then the problem is, let's say I had a phase that went all the way to like here, right? So I don't know if it's a big positive flow, or maybe it's a smaller negative flow. Okay. And so that's the ambiguity. And so there's something called VENC, which is sort of like that's the velocity which gives you pi phase, right? And so if your velocity is higher than that velocity, it's going to give you more than pi phase. And so you're not going to know which way the velocity came. This is an example here where they're looking at artery in the in your lungs, the pulmonary artery. And so here the VENC was set too low. So VENC of 15 centimeters says that 15 centimeter per second flow will give you a phase of pi. Okay. And what's happening in this person is there's flow that's faster than 15 centimeters per second, right? So it's going past pi. And so when it goes past pi, the algorithm just says, well, then you must have flow going the other direction. Okay. And therefore, you see in this vessel, you're seeing flow going both directions. Okay. So if you didn't know that this was the case, then you might think, oh, there's some weird turbulent flow in here. We need to like maybe do surgery on this person, right? Or there's a problem that maybe this is related to their symptoms. But in this case, they're showing you that if you set the VENC to now to 30 centimeters per second, so now that 30 centimeters per second gives you phase of pi, now everything is resolved. Okay. So from there, must conclude that these white spots, they must have had some velocity between 15 and 30 centimeters per second. Okay. So that's why sort of like radiology is sort of an interesting area of medicine because the radiologists have to know enough about the physics of what's going on to sort of to make sure that something is not an artifact and is actually reflecting your physiology, and also to make sure that the settings are set up so that they don't get fooled by physiology. Okay. So therefore, even setting this, physics parameter, they have to have some knowledge of what's the expected velocities that they're going to measure. Okay. So if they're in a very low flow region, let's say like the liver, they can set the VENC much lower, right? Because they don't expect really high flows. But if they're in the heart or in the lungs or something where there's high flows, then they need to set the VENC higher. Okay. So there's a really interesting interplay between physiology and engineering. Yeah.
But why you just said vent to like really high all the time?
Yeah, that's a great question. So let's say you set the VENC to like 100 all the time, right? But your flows are down like 1 or 2 centimeters per second, right? So then the phases you're going to get are very small, right? So then they'll be much noisier. Yeah. So you don't want to set the VENC too high, right? It's sort of like if I'm asking you to measure the size of, your fingernail, and I give you like a ruler that's 10 feet long, the precision is not going to be as good, right? You want something that's about the right length ruler. Yeah, but that's a great question. So these are some of the trade-offs that people have to make. Okay. And the aliasing isn't just an issue with, even with VENC, you can sort of have, and probably what you saw in that vessel is one of the causes is, there's laminar flow, right? So in fact, even within a vessel, right, you can have slower flow at the sides and strongest flow in the middle. And if you're not careful, you can have the middle flow get aliased and look at like it's going backwards. Okay. So the other thing you can do is you can do multiple Venn values, right? So then you keep the phase difference less than pi radians. So you can let the overall phase be more than pi, but as long as you do two Venn values, there's a way to like subtract those and also so get the measurement that you want. Okay. And then the other way we measure flow is something called the inflow effect. This is a really nice example of how I think we've talked about it before, where in medical imaging or even just science in general, a lot of times things just happen by mistake, right? Like you're looking for one thing and then something else happens. And so a lot of times in medical imaging, there are things that people consider to be artifacts, and maybe they try to get rid of them for like the research for 5 or 10 years is like, how do we get minimize this artifact? And then one day, sometimes it's a grad student, it's a student who's just new to it, looks at it and goes, "Oh, this is really interesting. I could use this to measure something." Okay. So a lot of the things that you see actually in the clinic started off as artifacts, and then someone just looked at it in a different way and said, "Oh, this is really interesting information." So that's as you're doing your career, it's good to keep in mind that, sometimes the things that you think are mistakes actually can lead to your solution. Okay. So just keep an open mind. Um, this one is based on sort of T1 relaxation. Okay. So we talked about before, if we have two RF pulses and there's the TR, if I wait long enough, then the magnetization recovers fully, right? But if I make that TR really short, then I don't give the magnetization time to recover, right? So if I imagine applying a lot of pulses very quickly, that's going to saturate or reduce my MR signal. Okay. So the inflow effect is basically what happens if I just apply pulses that only affect spins here. So, applying, so RF is only affecting things in that volume, and it doesn't affect things coming out from here. So as blood is flowing, only the spins here experience the multiple RF pulses, and the spins that are flowing in come in with fresh magnetization, right? They don't experience as many RF pulses. So what's going to happen is over time, you're going to see that the spins sort of that are flowing in are going to be brighter than the spins that were just static and experienced all the RF pulses. Okay. So the idea is this is the inflow effect. So if I'm a static piece of tissue, like brain tissue, I might experience 100 RF pulses, but if I'm flowing in blood, maybe I only experience like 50 or so, right? So I'm going to be relatively brighter than my surroundings. So that's the idea that we do repetitive RF pulses in the region, and the stuff that's flowing in experiences much less. So it should be brighter. Okay. And that's also shown here where it's brighter for the things that are flowing in and dark for the ones that are fully saturated. And so you can sort of see here, there's an obvious example where these bright spots are what are the inflow effects. Okay. So sometimes these are considered artifacts and you don't want them because they're very bright and depending on your imaging acquisition, they can sometimes bleed into the tissue. But if you imagine thresholding that image and doing what's called a maximum intensity projection and just sort of taking the maximum value along any plane. So maximum intensity projection is just, I can start from here. Let's say I want a maximum intensity projection. I can just, along every voxel path, I can just take the maximum value, right? And that's my MIP. So this is MIP, maximum intensity projection. And so you get these beautiful sort of images of the vasculature. And this, yeah, go ahead.
So you get some sort of 2D projection.
Yeah, it's like a 2D, it's a maximum. But it's not a projection like in CT where we take the integral. It's just you just take the maximum along any ray vector. Okay. Just a way of visualization that's quite used quite a lot in medical imaging. And so the nice thing is this can be done without contrast. And also you can also inject contrast into the subject and make the T1 even shorter. And then that can also help with the the contrast. Okay. Um, and then another area where inflow effect happens is, remember, this is what we call a spin echo, right? Okay, so we got a 90-degree pulse and a 180-degree pulse. And so that the 180-degree pulse is refocusing the spins. And so sometimes inflow effect can sort of still be an issue where if you have something with the spin echo, the blood is flowing such that it experiences the 90-degree pulse, but it's going so fast it doesn't experience the 180-degree pulse. So it doesn't get refocused. And so in that case, you can end up with these really black areas where blood is flowing fast. Okay. So just sort of giving you a taste of how um, we're starting to think about the interaction between the MR physics and also the physiology and things moving around. Okay. Great. So do we have any questions before we move on from there? Okay. All right. So I just want to talk a few minutes talking about noise and the main, just to give you a sense of, I think everyone has a sense of that noise makes it harder to see images. And this is from your textbook showing that with increasing noise, obviously the image becomes, the quality degrades, right? And at some point it's so noisy that you can't make a diagnosis from it. So the key is you're always trying this trade-off between if I want to really reduce noise, as we'll see, we can spend more time, but I don't want to spend too much time because that might make my exam too long or the subject is moving too much during that period. Um, One way we can reduce noise is you can blur the image, okay? And so this is showing that, if I have a lot of noise, and I just blur more, I can reduce the noise somewhat because essentially it's averaging the noise over spatial areas, but it's not really a great solution if you have a lot of noise. So the main thing you want to get across is that what we talk about is signal to noise ratio. So that's essentially look the signal over the standard deviation of the noise. And what it comes down to is this. So the most important part is this. It's always related to the square root of your measurement time. Okay. It also depends on your voxel volume, and then this is sort of your image contrast parameters, right? Like, if you want T1 weighted or T2 weighted or something like that. But let's say we've set the image contrast to what we want. The voxel volume is very important because that's just saying that as you make the voxels smaller, then they're going to be noisier. And so you don't want to pick two. So that's the other trade-off you always have to make. You would think, oh, I always want the highest resolution possible. But it turns out if you do that, you're going to give up a lot of SNR. So you want to pick the right voxel volume such that you can sort of see what you need to see, but not make it any smaller than that. And then what we're going to talk about, spend a few slides talking about is measurement time. Okay. This is essentially, you can think of it as, remember the ADC, which is sort of digitizing all our stuff. Essentially, the measurement time is the amount of time that ADC is on. Basically, how much time are you collecting data? And there's a few things. Next is the number of averages. Okay, so we'll talk about that. And read is sort of how many points we're acquiring along the readout direction. And so, for example, in the spin warp case, it's sort of how many samples I'm acquiring along this gradient. And phase is the number of phase encodes, how many lines I'm acquiring, right? So the number of phases I'm acquiring, so that is actually affecting the time. And then delta t, remember this has a delta t sampling, okay? So n read times delta t, right? So tau x is going to be n read times delta t. Okay, so that's the full time that readout gradient is on. Okay, so basically this is all this time. Each of these is n read times delta t, and then I do n phase of these. And that tells me how much time I'm spending acquiring my data. So let's take a look at examples of a few of these. And in fact, we've talked about some of these things before, but today we're going to talk about next. Okay, so that's one parameter that people can set. And the other parameter that we're going to talk about, let's see, is it on this one? Bandwidth. Okay. So we're going to talk about what bandwidth means. right? So previously we've talked about things like FOV and slice thickness and also resolution, frequency, and phase. So today we're going to talk about NEX and bandwidth. All right. Oh, we've also talked about flip angle. So you sort of see here that the user can set the flip angle. They can also set the echo time. Um, in this case, the TR, they're not allowed to set. Um, Typically, what you'll see is when you're doing an MR protocol, oftentimes there might be some fields that are grayed out, and that just means that you're not allowed to set that parameter. It's set for you. Okay. So what is bandwidth? Bandwidth is just basically just 1 over delta T. Okay. And so that's basically the higher bandwidth just means you're going faster, right? And so your time measuring time is going to go down with that, all things being equal. Okay. And so here's the idea. If I spend a lot of time measuring, then I have a very low bandwidth. Okay. And if I go through K-space really fast, then I have a very high bandwidth. Okay. So low bandwidth is I'm spending a lot of time measuring. Okay. I'm going through K-space fairly slowly. And then high bandwidth is I'm just like zipping through. Okay. And so let's look at the effect of that on the SNR. So here I'm going from receiver bandwidth of 30 to 600. And you zoom in on these images, I have pretty high SNR with the low bandwidth. Okay. And as I go to the high bandwidth, you can sort of see how here this is a lot grainier there, right? You guys see that? Okay. As compared to here, where it's pretty less grainy. Okay. So that's the effect on SNR. So then the question is, why wouldn't you always just use, why not always use low bandwidth? Okay. And so it turns out the answer is because like the more time I spend, right, there's a couple of things. Things are relaxing, right? Things are decaying away. Also, things are moving around, right? And so all these sort of, once we move away from ideal objects, there's a lot more things that can happen. Like there can be dephasing of the spins or, flowing spins and diffusion. And so there's going to be a trade-off. All right. And we'll take a look at some of that. So this is a really nice example here, where here I have a bandwidth of 60. Okay. And if I have something where it's a normal brain, I get a nice SNR here, high SNR. And here I have a bandwidth. So here's a bandwidth of 130 versus 300. And so in this case, I do get an increase in SNR, so high SNR. But let's say we have someone with a high metal artifact, like the braces, right? So now if I do a bandwidth of 60, there's more time for that metal to dephase the spins and screw up the spins. And so I end up with these really strong artifacts. Okay. Now the bandwidth of 400 doesn't get rid of all of them, but you can sort of see it's actually at least correcting it. They're at least reduced somewhat. Okay. So there's always this trade-off between there's certain advantages of high bandwidth versus low bandwidth. The other thing you can play with is next. So you might say, okay, I want to keep a high bandwidth to get my image quality, but I want to increase the measurement time. And so here the idea is you just repeat your measurement many times and then you just average the data. Okay. So you might take acquisition 1, acquisition 2, and then you average both of the same line in K-space, you just average that. Okay. And so here's an example here where if I do a next of 1, um, it looks pretty good, but it's sort of grainy here, right? And if I just average 4 times, you sort of see I've gotten rid of some of that graininess. Okay, so that's where it comes in. Basically, the next increases my measurement time, and so I can use that. I can still use a small delta t, and I make up for that by just increasing the next. Okay. And here's another example where we have next of 1. Um, Yeah, so basically high SNR, but the resolution is not so good. And then low SNR, okay. Um, where I basically, in this case, I made the voxel size smaller, right? So this matrix size increased. So this is now smaller. Okay. So in this case, I can make up for that by just increasing that. Okay. So this went down, so I increased next. So I get my high resolution and high SNR, right? So these are some of the trade-offs that clinicians can make. Um, and you can play the same game with bandwidth. For example, you can keep your high bandwidth, but you use a nex of 3. So you get both the high SNR and it's sharp. Whereas if you didn't do the averaging, you would have low SNR, right? So there we're trading off the nex versus the delta T. Okay. Okay, so that's really sort of all we're going to do in terms of subject matter. And now we're just going to spend a few minutes talking about the future of fMRI. One of the things that's sort of been happening a lot over the last 10 years, and it's going to continue, is that if you look at sort of the cost of magnets, it's still a large cost of a magnet is the big magnet and the cryostat, which is the part that keeps it cold. Okay. And so typically, if you're going to buy a magnet, it's roughly $1 million per Tesla for a traditional magnet, right? So if I'm on a 3 Tesla magnet, you sort of have to budget $3 million, right? And then in addition to that, you need to prepare the room, and that might be like another $1 million to prepare the room. So it's really expensive. Okay. So some of the things that people are looking at is, well, can we reduce the cost of the magnet? And also, can we make it so that the siting cost is not so high, right? Like one of the things that increases the cost a little bit is if you have a lot of helium, you need to figure out a way if the magnet quenches or loses its field, you've got all this stored power, right? And you got to blow off its steam somewhere. So you need a quench pipe. Like if we had a magnet here, we'd have to have a pipe that would send the helium outside. Okay. Um, and that can be in this, for example, in this building, right? They may not allow us to have a pipe just going out the window. You might have to go all the way up to the ceiling, right? And that would be very expensive if we had to retrofit this room and put a quench pipe in this room, that could cost a lot of money. Yeah.
So like prefabricated magnets, kind of like they sell prefabricated ones by the entire group.
Yeah. Well, you can get them in a trailer. Like if you want to, like if someday you want to get your own MRI system, then you can buy in trailers. And so, in fact, here at UCSD, sometimes when there's a need for more MRIs, but there's no building to put them in, they'll just rent a trailer. And so the manufacturers have figured that out. Or if there's special events, like I think I'm not sure if it's been decided, but I think, for example, at the Olympics are coming to Los Angeles in 2028, and I think there's probably going to be a portable MRI somewhere there. Okay. Yeah. So yeah, if you have enough money to buy a MRI, that's one option. You can just buy a trailer and put it in your backyard. You just have to have enough power and, cooling to support it. Yeah. Um, One of the things that is that there is a lot of um, sort of inequality, I would say, in terms of, where MR can be done. Typically, traditional MR needs a lot of infrastructure. You have to have very good power, very stable systems. And so in this one, which I think is probably 5 years old now, obviously Germany has a lot of MRIs per capita simply because, Siemens is there. And so there's a lot of MRI manufacturing in US as well. And then certainly areas like Ghana and India are, there's not much presence of MRI done. Okay. So one of the things that people are doing is trying to make it so that the magnet is, you don't need as much helium. And so you have these what are called conduction cooled magnets that are just really good at sort of taking heat away from the magnet. And so that's one trend. And in fact, these are 3 magnets that were just introduced this year. Okay. So one from GE, one from Siemens, and one from Philips. The ones from GE and Siemens are 1.5 Tesla, and the one from Philips, which was just, it's not available in the US yet, and whether it'll be available or not, it's not clear, but yeah, I think it was just announced. There's a big conference going on right now in Chicago, and I think it was just announced. And so you can sort of see this uses only 0.7 liters of helium. This is 7 liters of helium, 20 liters of helium. Okay. As compared to a normal conventional magnet might be 1,000 to 2,000 liters of helium. Okay. And so that means that it's much easier to site these magnets, right? You're not going to have to worry about this quench pipe and everything like that. It's also going to be a lot less expensive because helium is quite expensive, right? It might be to refill one of these magnets, it can be anywhere from 100 to $200,000 just to refill the liquid helium if you lose all the helium. Okay. So I think as sort of things evolve, you're going to see much more of these sort of low helium magnets. Okay. The other thing that we've talked about, and I've shown some of this before, is there is a lot of interest in more portable magnets or smaller magnets, or even magnets that are sort of, if you make magnets smaller, for example, for like neonatal, like imaging babies, you don't need a big magnet. So having a smaller magnet lets you not have as much helium and you can sort of optimize the design. Okay. And then there's also this sort of magnet, this hyperfine magnet, which is portable. We can bring one in here and we can image you, and it doesn't require any other setup. And what's really made this possible, and sort of the other area that's going to continue to grow, I believe, is the idea of these portable magnets. They have a much less slower SNR, and their image quality with conventional reconstruction is not that great. But if you add deep learning, okay, advanced recon, remember, deep learning has the advantage that it sort of knows what your images should look like. It's got a really good prior distribution on your images. So it can see through artifacts and sort of get rid of artifacts for you. So if, for example, this is going from one generation of software to the next generation of software and just showing that it's the same data, but just making the software better, you can get a better image. Okay, so that's been really important for these sort of lower sort of, the input data is not of high quality, but you can make up for it with better reconstruction. Okay, making better use of the information you have. Yep. Our babies.
Why are babies getting?
Um, well, I mean, for example, if there are, if, for example, the baby is born with some issue, then they will get an MRI. And then there's also, from a research point of view, people are doing research scans on babies to sort of understand development. Yeah. Yeah. But from a clinical point of view, it's sort of like, it's just, for example, you might have a baby born with like hydrocephalus, a lot of fluid in their brain, and you just want to sort of see how they're doing. Yeah. The other thing is MRI is, um, if especially in certain populations, if you have a choice between MRI and CT, you're probably going to still go with MRI because of the radiation dose, right? And especially if you have to track someone over many, if you want to scan someone every week or something, you're not going to do that with CT, right? Especially, there's a special concern too with younger populations because their cells are dividing and growing so fast, right? So any radiation you put into them is much more likely to cause a mutation, right? Whereas if someone is like 80 years old, it's like, okay, even if you cause a mutation, there's so many other things wrong with their body already. So it's like, it's not going to have as big of an effect. They probably already received so much radiation just from cosmic rays over their lifetime. So in general, for babies, if you can do MRI, it's generally, you would prefer to do that. Yeah. Okay. This is just showing, I think also just from that hyperfine, just showing how things improve with software. So this is like version 1.6 of their software and version 1.9 of their software. You can sort of see here, for this, so DWI stands for diffusion weighted, right? So that's using what we talked about last time. So this is the low field. So the high field is sort of a conventional scanner, what it would do. And the low field is sort of like this portable scanner. And you can sort of see with this version of the software, it's not really doing a very good job. And then if you improve the software, you can actually recover the image. Okay. Similarly, for this low field fluid imaging, it's sort of improving the image quality just by improving the software. Okay, so that's a big opportunity for as people figure out how better to sort of use deep learning, then that gives you the ability to design systems where the hardware is maybe not as good as what it used to have to be. Okay. And then finally, we've talked about sort of these traditional magnets, which have like superconducting wire and helium. And there's an idea that if you really want to make things portable and have them more widely distributed, then maybe you want to look at other designs for magnets. Okay. And here, what they've done is basically they've taken a bunch of permanent magnets, okay, using what are called Hallback magnets. And then they basically just arrange them in a fashion to create a magnetic field. But it turns out that the magnetic field is far from uniform and has a lot of issues with it. But the hope is that with advanced recon, if you know what that field is, then you can undo all those non-idealities and get back to your image. Okay, so that's where it's going. And even this one here, this is sort of like a hair salon kind of magnet, right? Basically, so here's the magnet here, and using also, once again, these little permanent magnets. And it's very non-uniform, and it's not, if you just had Fourier transform theory, you would not be able to reconstruct your image. But if you are able to sort of take sort of linear algebra approach that we introduced you to, and then sort of combine that with deep learning and just sort of solve the whole inverse problem, then you actually have a chance of recovering. Okay. So I think what we'll do is we'll end here. So we can end quite a little bit early today and give you back some time to work on your project. So any last questions before we end for today? Okay. So I think hopefully if anyone needs feedback on your projects, feel free to ask for feedback. I think in past years, there's people have asked for a lot more feedback, so feel free to ask for feedback. And also, especially if you've sort of hopefully you've learned something from the course, and I think Professor McVeigh and I are very happy that we're able to share sort of what medical imaging can do. There are, I think, evaluations for the TAs and both instructors. So if you have some time, take some time now to fill those out. And for those of you who are live question sessions. We'll see you on Zoom on Tuesday, and we'll send out more details about when your group needs to show up. Essentially, you should probably just need to be there within 30 minutes of your time slot, just in case we need to change the order. And if we don't see you, then have a very good holiday and good luck with your courses or your future curriculum. Yep, question.
It's on Zoom, the live question groups.
Yeah, I think we decided just to make it by Zoom because it'll make it logistically a lot easier. Because although in person is nice, it's just sort of on Zoom, it's just much easier. Yeah, and I don't think anyone will mind not showing up. Yeah. Okay. Any questions before we end? Okay, if not, I'm here to answer questions, and otherwise we'll end the recording now. Thanks.